For electron configuration, we can do a predictive electron configuration, which will be good for most of the elements, certainly the main group elements. But for the transition elements, and especially the inner transition elements, there are many locations elements where the predictive system of reading the location from the periodic table doesn't give us the actual electron configuration that we have. So in the transition metals, we can shift some of the s electrons over into d. Down in the inner transition elements, we're shifting first the d into the f, because we would predict one d electron over into f, or we can also shift the s electrons around to some degree. There's only two spots that I'm going to want you to be able to state the actual electron configuration. In column 11, the noble metals, copper, silver, gold, and Roentgen. For all these elements, the predictive electron configuration would say that there would be 2 s electrons and 9 d electrons. These are all finding that it is more energetically favorable to shift one of the s electrons over into the d, so we end up with a 5d10, not 5, but a d10, and only a S1. The other spot doesn't go down the whole row, but for chromium and molybdenum in column 6, group 6, the predictive electron configuration would be saying that there's a 2 s electrons and 4 d electrons, and again it finds it energetically favorable to slide one of those s electrons into d, so we end up with a D5, the half-filled sublevel. So we're shifting S into D to give us a half-filled sublevel for these two elements here. Electronegativity. This is what we use in polar compounds to determine if bonds are polar or non-polar. So if they share electrons equally or share the electrons unequally. Electronegativity has its highest value with fluorine in the upper right part of the periodic table, not with the noble gases, which do not react, but with fluorine that reacts. So fluorine is the most electronegative element, so the electronegativity increases toward the upper right of the periodic table and decreases toward the lower left of the periodic table. So we need to know the trends on electronegativity. So the electronegativity increases as we go up any column, and it increases as we go right across any row, with the maximum being the highest with fluorine. So we need to know the electronegativity trend so we can easily tell between two elements which of those two elements is going to be more electronegative, which one is going to be more likely to hold more the negative charge. So metals, just a quick summary of metals and a couple groups of elements here. Metals tend to be shiny. They conduct heat, they conduct electricity. They tend to be malleable and ductile. Malleable means that when you hit it with a hammer, they bend instead of shattering. Ductile means you can pull them into wires, which we use metals for, to make wires. Metals tend to have high melting points. We only have one metal that's liquid at room temperature, mercury. Metals tend to have low ionization energies. They ionize easily to form cations, positive ions. Most metals will oxidize easily, either in air or by acid. So we know that metals, iron-based metals, rust. This is the oxidation of iron by air. Most metals would react with acid except for the noble metals, copper, silver, gold. Metals react with nonmetals to form ionic compounds. So ionic compounds are the reaction of metals with nonmetals. Metal oxides, a lot of metal oxides are basic. That means when we dissolve them in water, we form a metal hydroxide. Metal oxides can also show their tendency to be basic by reacting with acids to form salt and water. Nonmetals, we have a smaller list of nonmetals. Nonmetals tend to have low melting points. Several of them are gases under normal conditions. We got 7 of our nonmetals form diatomic molecules also. So that is the most stable form under normal atmospheric conditions. Nonmetals have high electron affinities. That means that they readily form anions, negative ions. And this is especially in reaction with metals. When we only have nonmetals combined with nonmetals, we form covalent compounds or molecular compounds. The oxides of nonmetals tend to be acidic. So carbon dioxide dissolved in water is carbonic acid. Sulfur trioxide dissolved in water is sulfuric acid. Sulfur dioxide dissolved in water is sulfurous acid. Nitrogen oxides dissolved in water give us nitric and nitrous acids. The acidity is also shown by the tendency of the oxides of nonmetals to react with sodium hydroxide or to be absorbed by sodium hydroxide in solution. So we can use sodium hydroxide to react with or absorb carbon dioxide out of air, and we use this to in rebreather scuba apparatus as a way to remove the carbon dioxide to prevent a toxic environment from the air. So alkali metals, column 1A, column 1, are the alkali metals. These are extremely reactive metals. Hydrogen is usually on top of this group, but hydrogen is a nonmetal. Hydrogen is not an alkali metal. So alkali metals, the density tends to increase as you go down the column. This is true with all groups because the atomic mass is increasing as you go down the column, and the atomic mass is increasing faster than the atomic size, atomic radius. Melting point and freezing point also decrease as you go down a column. The alkali metals are extremely reactive. These will react with air and water. They react with water to form hydrogen gas along with the metal hydroxide. They're very vigorous reactions, very exothermic reactions, and they can ignite the hydrogen gas and create explosions in the process. Alkali metals have very low ionization energy. They ionize readily to form the +1 cation. And alkali metals can react with oxygen in a variety of ways to form different types of oxides. So types of oxides we can get, there's a standard oxide, which is a O with a 2- charge. We can also end up with a peroxide, which is a O2 with a 2- charge. And for a couple of the elements, we have a chance of creating a superoxide, which is O2 with a -1 charge. The peroxides and the superoxides tend to be unstable. They are likely to react under certain conditions to convert back to the oxide form, potentially in a very violent reaction. Melting points and boiling points of our alkali metals. We see that the melting point decreases as you go down the column. Boiling points also decrease as you go down the column. So the heavier elements will melt quicker than the lighter elements. Ionization energy, first and second ionization energy. First ionization energy has only very slight change going up and down the column. The second ionization energy shows a more dramatic change. Second ionization energy is representing the inner core electron. That's why the second ionization energy is so much larger than the first ionization energy. And it's highest for lithium for the second ionization energy and decreases as you go down the column. These atoms get bigger as you go down the column, both atomic radius and ionic radius. We see, of course, that the ionic radius is smaller than the atomic radius, so the cation is smaller than the neutral atom, and they get bigger as you go down the periodic table. Alkaline earth metals are harder, more dense than the alkali metals. They have higher melting points, higher ionization energies, and they are less reactive, such that beryllium is non-reactive with water or steam. Magnesium does not react with water, but it does react with steam. So steam has enough energy to initiate the reaction with magnesium. Calcium and the other heavier alkaline earth metals will react with water to form the hydroxide plus hydrogen gas. So the reactivities of the elements increase as you go down the chart toward the heavier elements.